Hey guys, in this next video, let's start showcasing some differences between the assembly language we've utilized thus far in this course and the C programming language. So to do so, let's just write a simple C program. And in that program, let's do pretty much the most basic thing we know how to do in the context of this course. Let's map the logic values specified by the dip switches located on the out-of-the-box switch and LED backpack directly to the LEDs also located on that backpack. So basically, whenever the logic value dictated by a single switch it goes low, it will turn on the LED corresponding, or LED directly above or below if you're looking at the backpack in a different way. The LED will go on, and then correspondingly when that LED, or when that switch opens up, that LED will turn off, and that will be the case for all of these corresponding switches. So super simple, but let's start to see how we would write something like this with the C programming language. So let me first switch over to my Atmel Studio code window. So within Atmel Studio, I have a file for us to start working off of called Introductory example.c. And in this file, and in all files that I'll try to write for this video series and beyond, I'll try to devise and maintain a meaningful structure for the code that's going to exist in that file. So that's why you see these sections here. And I will recommend that you all try to do the same whenever you all write code, for any programming language, in fact. But the sections that I have, I'm not going to really talk too much about right now, but I at least wanted to begin to expose us to how our code's going to be organized. And again, not going to really talk too much about the particular sections, or most of them for this video. But the first one I will mention, beyond a header having some information about the file, is this dependency section. So the dependency section is basically I'm going to use to house any preprocessor directives that specify for the preprocessor to include some other files. So just as in assembly contexts, when we included the ATX-Mega 128A1U def.inc file, which provided us with some useful symbols, we're going to have a very similar file for AVR file called io.h that we'll include. And this will ultimately include similar symbols and useful labels for various things that we want to use in context of our microcontroller. Now, the only other thing I want to note before we actually look at this file is that besides the preprocessor directive and assembly also being called include, in assembly it was prefixed, the include portion was prefixed with a period. In C contexts, preprocessor directives, instead of periods, are going to be prefixed with a pound symbol. So just note that right now, but we'll talk more about preprocessor directives later on. So the other difference besides including this dependency file and the one in assembly contexts was that whenever you would create an assembly project within Atmel Studio, by default, the dependency section should automatically be populated, I believe, with those assembly, with that relevant assembly include file for AVR. Now in C projects, unfortunately, by default generally, the dependency section will not actually be populated with files. In other words, this drop down or this arrow will not exist yet. So what you need to do is first build some file within your project. And if you are to add a file within Atmel Studio by default, or use a default created project within Atmel Studio, you can actually go ahead and hit build right away, and it should build successfully, I believe. And then when you do that, the dependency section should automatically be populated with all the relevant files. And these files, we'll see if we open up, there's actually quite a few, more than we're probably accustomed to in assembly contexts, but we do see this io.h file that we're referring to over here. So let's go ahead and open it up and see, what does that look like? So we got some kind of header, and then we see, if you scroll down, a bunch of preprocessor directives, again prefixed by this pound symbol. But if we actually look through, we won't actually find any symbols similarly named and meaningful as the other include file. So what's going on is, I told you all that we're going to have that, so why don't we have that in this file? Well, what ultimately ends up being the case is that this file will choose another include file based on the relevant device that you selected for your particular project, and it will include this other particular include file that includes particular symbols relevant to that specific device. And in our context, that's ultimately going to be the iox128a1u.h file. So it's only going to include this for our particular processor. If we open that up, we get another file which ends up being humongous, and this is a file that you will look through many times throughout the remainder of the semester. But this is going to be the file that provides us with those similarly named constants and labels, symbols, etc. for our microcontroller. And we're going to, instead of unlike how we did with assembly context, we're going to require that you all use any predefined symbols defined within this file whenever they can be applicable. So just so that your code is more readable and so it's easier for any course staff to help you all out with debugging your code, etc. This we want to enforce you all, even for your own good, for learning how to write more readable code. We're going to enforce that you all reference and utilize this file whenever applicable. So we're going to look at this file more later on, but I at least wanted to show us where it exists and how to get to it. So let's go back to introductory example.c. Now, the last thing I'll note about dependencies, there are going to be other dependencies that we include in general, at least one other AVR file, which we're not going to talk about right yet in this video, but at least wanted to show us one dependency. And besides these other sections, the other main section I want to mention for this video is that associated with the main program. So I'm going to have a section dedicated to main program. And in this case, the main program, as I mentioned before, in C contexts, the main program, or basically the entry point into some program for our microcontroller, is going to be derived from some function. In this context of C, this is going to be called a function. Some C function named main. That's just going to be a conventional name that Atmel Studio is going to detect. Hey, that's going to be this entry point of this program. Now, for this function, we're not going to talk too much again about functions yet, but basically the definition for this function, or the function, the thing that the function is to be associated with, the code itself within the routine, is going to be defined within this left brace and right brace, or some left brace and some right brace following this function header. So in this case, I just want to tell us that in general, any code segmented between a left brace and right brace is going to be called a block of code. And just as in assembly, there can exist other blocks of code or other routines, just as in assembly where we had subroutines, interrupt service routines, etc. We're going to have similar sections or subdivisions of code in C context. But for this simple program here, I just want to have a single routine all within our main routine to accomplish everything that we want for this program. So besides that, let's start getting right into the meat and potatoes of the program. So let's remind ourselves, for this program, all we want to do is basically map the logic value specified by the dip switches on the switch and LED backpack to the LEDs also located on the switch and LED backpack. Now to do so, in general for assembly, we know we do a couple things. We initialize the relevant I/O ports, which in this case, port A is going to be corresponding to the dip switches and port C corresponding to the LEDs. And then beyond initializing the I/O ports for this simple example, what we want to basically do is just read from the relevant in register on port A or port A in, and then map that value. I'll scroll down and show, I'll reference this in a second, but basically we want to continually just load from port A in and map that value loaded from port A in to port C out, which is ultimately going to correspond to the relevant logic values that dictate the logic levels of the LEDs, or the activation levels. So in this case, so beyond, before I get into this, I guess, let's first just focus on the starting portion of our code where we just want to initialize the relevant I/O ports. So an example way of how we would do that generally with an assembly, we would simply just load some register with the value hex FF in this case if we want to change all the pins. And then say even though it might not be pertinent for this appropriate application, let's just say that we want to initialize all the LEDs to be turned off. To do that, we would generally write to the outset register. And with this hex FF, it would distinguish that all of the bits within the relevant out register would be set to be 1, which would then ultimately correspond to the LEDs eventually turning off. And then after this, we would then write to the relevant dir set register, again, hex FF being applied to that register, which would then set the relevant pins corresponding to that port to all be outputs rather than inputs. Now in C, I'm just going to get right into how we start translating something like this into the C programming language. So in C, I'll go ahead and write something out for us and then talk about it. So C, if I write port C outset equals hex FF, I'm going to tell us right away that this line of code is ultimately going to translate into these two lines of code in our assembly representation. So in C context, from wherever we're accessing memory, we're going to see in general that we want to think that the memory location, that if we're writing to some memory location, is generally going to be the first thing that we write in some line of code or some statement of code, as we're going to call it generally. So in this context, there's going to be a label, port C outset, just as before, except now you see I probably am utilizing this dot notation. I'm going to access this port C outset label, and I'm going to set that label, which ultimately is going to correspond to the memory location for the outset configuration register within port C. I'm going to set that memory location equal to the constant value hexadecimal FF, which again prefixed with 0x is also going to be translated to hexadecimal FF just as before. Now this overall line of code is going to be translated, or it's going to be referred to as a statement within the C programming language. And whenever we terminate a statement, or wherever we want to specify to the compiler, hey, that's my complete statement, we terminate the statement with a semicolon. So overall, this line of code in C will ultimately see that this will translate into some form of assembly code that does something like these two lines of code. And we'll talk about that a little bit coming up in a few minutes. But I at least want to just throw us right into the syntax and see how we could do something like these two lines of code. And similarly for this, for writing to the dir set register, we would write to port C dir set and write hex FF. Now, it's probably useful for me to mention, why am I using this dot notation rather than this underscore notation? Well, there's going to be a couple reasons why ultimately, but the main reason is going to be that with this dot notation, I'm not going to really explain why this is the case yet, but with this dot notation within C context of Atmos Studio, it's actually going to provide us with a automatic listing of all of the configuration registers for that relevant module or system, which is going to be helpful sometimes. And in general, I'm going to try to manipulate or utilize this autocomplete nature whenever it's useful for me or more efficient for me writing my code. But that's the first primary reason we're going to use this dot notation. And beyond that, I'm not going to mention anything else right at this moment. But it actually is the case that the underscore notation is still defined. It's a relevant symbol defined within, in our context now, this iox128a1u.h folder file. But I'm going to recommend that you all try to use this dot notation again for a couple reasons, but just take my word for it right now. So this dot notation, beyond that, let's go ahead and see we've now configured, I'm telling you, the initialize the LED or the port corresponding to the LEDs. Now let's do the same for the inputs, or the switches. So we know that we would want to access basically the port A dir clear register. And to do that, we could do port A dot dir clear in this context. And again, setting all of them, we want to set that entire memory location equal to, set it equal to hex FF. So basically that's all we have to do in C to translate this into something, an assembly that we want. And now we can maybe see that this is not exactly too many lesser lines of code yet, but we'll see later on in C. In general, C is going to allow us to condense a lot of our program implementations into a lot lesser lines of code than if they were implemented in assembly language. So now getting to the actual rest of this program, where we said that all we want to basically do is forever continually read from the port A in register and then write that value that we read into the port C out register. It's actually going to be really trivial to do in C. So we also, on top of this, are going to have this, we have this looping nature that we know we had to implement in assembly. Before I talk about that, let's just say how we would do this whole mapping of port A in to port C out. Well, just as before, where I mentioned, let's think that the memory location that we're trying to write to, let's think that's the first thing that I want to be specifying in my C statement, my C line of code. So let's go ahead and say that port c.out, well, we could guess that port c.out, if I want to set that equal to some value, well, before we set some constants equal to some memory location, but maybe we could do the same with reading from some memory location. So maybe if I wrote port a.in over here, maybe this would translate to having the compiler load from this memory location and set that memory location, whatever's in that memory location, equal to, this memory location equal to whatever's stored within that memory location. And then again, let me say I terminate my statement following that with a semicolon. It actually turns out this is exactly what the compiler is going to do. It will translate into some form of code that ultimately does the same functionality as this 2 lines of assembly code will do. And again, we're gonna actually see some generated assembly code here in a minute. But to finish this basically program overall, in this simple program, we need some way for this looping mechanism to actually, or for the compiler to know that this needs to continually occur. Now again, with an assembly, we would create some kind of label and then manually jump to that label whenever we wanted to. If in this context a continual loop, we would continually jump to that label. Now we want to do something similar in C, but we're not gonna manually create labels anymore. What we're going to use are special statements, sometimes referred to as looping statements or just various other things. I'm going to refer to them as looping statements right now. But a conventional way of doing this kind of continual loop over and over is we're going to use this particular statement called the while statement. Now, ultimately, again, I'm not going to talk too much about this, the semantics yet, but I'll go ahead and write out what will accomplish what we want. If I were to write while parentheses, left parentheses, right parentheses, and in this parentheses write a 1, and then I were to start a block of code, again, where the block of code is dictated by left and right brace, and I were to put this code, since it didn't automatically do it, let me cut the code and then paste it in there. So if I were to put the code that I want to continually execute within this block of code, and ultimately what's going to happen is that with the semantics of how the C language is built with while statements, when a block of code immediately follows some while statement, will ultimately get translated into assembly code is this nature of a loop where whatever's in the body or the block of code will get executed for however long some condition is true. Now, in this case, in general, the condition is specified by some expression within this parentheses. And again, this may be confusing right now, and I expect that it will be, but try not to spend too much time on it. But ultimately, what's going to end up being the case is that conditions for looping statements, which while is not the only looping statement that exists within the C language, conditions will get evaluated to be either true or false. And in C, true statements are any statements or expressions that ultimately get evaluated as being non-zero. So in general, the expression will get a value of either some integer value, let's say. And if that value is non-zero, it will be considered as a true expression. And only when that expression is considered or evaluated to 0 will it be considered a false expression. So if I were to write, in this case, the constant expression 1, which will get translated to the constant value, integer value 1, what's ultimately going to happen is that this condition is always going to be considered true. And at the end of the day, what that's going to mean is that this body of code, this block of code, is always going to be executed because this condition of this loop is always going to be considered true, and this code is always going to be, as long as that condition is true, this code is going to be executed. So in this case, this is a conventional way you'll see of doing some kind of infinite loop that we want to have happen over and over and over and over. So in this case, this is pretty much all we need to write for our C program to implement what we want in terms of hardware. Now, to save time, I'm not actually going to show this running on our board just to save a little bit of time, but I will show that this program builds successfully, and you can try this on your own or take my word for it that this will translate into what we wanted to be implemented in hardware. But what I do want to do now for the remainder of this video is see the actual assembly code generated by the compiler tool within our Atmos Studio toolchain. Now, previously, remember, we required that we turn off optimization for the compiler. And again, to do that, we would go to Project, Properties, Toolchain, and then under this avr-GNU C compiler section, we would go to Optimization. And then under Optimization level, we would drop down this listing and then go to None or -0. And this would basically prevent or tell the compiler to not optimize or not to perform any kind of optimization when it is translating C code to assembly code. And again, just to let you know again why we're doing that for this course, we're requiring that you all do that because we want to create some situations in which it will be required that you all write some efficient or effective C code. And we want to show you how, in general, when you're writing for systems such as that contain microcontrollers, and in general, you sometimes need to be mindful of what kind of C code you write. So we want to try to create situations in which you need to be mindful. So we're going to require that you all have no optimization. But another side effect of having no optimization is that the code generated by the compiler is going to be somewhat inefficient, or sometimes it will actually do things that we wouldn't necessarily implement ourselves if we were to write assembly code. So I want to show it and highlight that fact now with this simple program that we wrote. So I'm going to go ahead and how I want to see the assembly code generated. The manner in which I'm going to do so is by start debugging my project. And this is the only way I know of how to do it at the moment, but there might be some other way. And then once we start debugging, I need to pause the debugger. And then within the debug window up here, I want to go to Windows. And then at the bottom of this tab, I'll find disassembly. And this is basically the Atmos Studio will generate a listing of disassembly code from the relevant process that the compiler went through. And this will be helpful to see sometimes what kind of actual assembly code is generated from our C code. And I'm not going to spend too much time on this disassembly in this video, but I want to highlight a few things. The first maybe interesting thing to highlight is that this disassembly code in general is going to list out the entire program memory map for our microcontroller, or at least the relevant portions of it. So what would be interesting to note is that the program memory address 0, maybe by default, has this memory location, or in this memory location, which we know now corresponds to the reset vector within our microcontroller, there is a assembly instruction listed here that stands for jump to address hex FE. So basically, disassembly is telling us that at that program memory location, there is the assembly instruction corresponding to the name jump and then the address hex FE. What's interesting about this is that we can remember and hopefully recognize that FE is the first memory location following our set of interrupt vectors for our microcontroller. So by default, the compiler, and ultimately it's going to be really the linker tool within our tool chain that does this kind of memory mapping of code, but it's going to automatically, set up that where to specify where our program is to start within program memory. So that's one useful thing that we don't have to specify anymore. But beyond that, if I were to scroll down, there's a lot of stuff that's not really applicable for this program. Actually, at FE is not our start of our program yet. It'll show us whatever source file or whatever file has some relevant code, it'll have this kind of nice subdivision within disassembly to tell us what file the following assembly code that you all are looking at is generated for. In this case, at FE, which again is the start after the interrupt vectors, there's some other file that is by default utilized by Atmos Studio, which we're not going to talk really at all about right in this moment. But I want to actually find our relevant file. So my relevant file, which again ultimately stored in introductory example.c. So whatever follows from this, it's going to be nice and show us sometimes some C code that was written, and then following that C code is going to show us some assembly code that was generated for that C code. And unfortunately, it's not always necessarily accurate, or it's not always meaningfully structured, depending on the C program written and on the optimization level of the compiler. But in this case, it should be relatively fine. So port C dot outset equals hex FF, we want to see what assembly code was generated for that C code. Well, it turns out the following C code was generated for that C code. The following assembly code is generated for that. So in this case, we can maybe, if we look at this, see it doesn't look exactly how we might implement the following, this code in assembly. Before, we would maybe just do a LDI hex FF into some register and then STS directly into port C outset. But here, with no optimization, the compiler actually is generating this LDI instruction, these two LDI instructions that load R24, R25 with hex 40 and hex 6 correspondingly, which we may not be apparent why we're doing that yet. And then it's setting register R18 to be FF with the SER instruction. And then for some reason, it's moving a word of information from R24 and R25. So if you're not familiar with this syntax, this is basically going to move R24 in the consecutive register next to it, R25, into the pair of registers R30 and R31, specified by this starting R30. So it's going to move this hex 40, hex 6 into R30, R31, respectively, for some reason. And then it's going to use this std instruction, store with a displacement, using now the z index plus some offset 5. And then it uses this value hex FF from register R18. So maybe we can imagine that storing this hex FF, this must be the port C outset memory location. And it actually turns out that that is exactly the case. But how do we know that? Well, it turns out that if the key thing to mention, maybe realize at first, is that this move word instruction, when it moves this seemingly random value hex 6, hex 40 into R30 and R31, remember that R30 and R31 correspond to the Z low and Z high registers. So in Z being our one of our primary indices that we use to point to memory locations, so somehow Z, for some reason, Z is getting pointed to the memory location hex 640. Well, if we were to do some digging, there's a few ways we could figure this out. But if we were to maybe go to, let's say, the relevant include file, iox128a1u.h, and open that guy up, if we were to search for hex 0640, we would actually find that in a couple places, it alludes to the fact that hex 640 is given, this value is given the symbol port C dir. So this hex 640 is given this, this symbol port C dir is associated with this value hex 640. So why port C dir though? Well, it turns out that in general, one common way and one of the reasons that these memory locations are structured how they are with some system is that we can see that all of the port C memory locations are jointly connected together and offset one away from each other in each case. So basically, consecutively in memory, all of the port C configuration registers are mapped to memory. So when we actually have this loading to port C, and then we go back to disassembly and see that, okay, well, if Z is pointing to that port C dir, memory location hex 640, and then there's this offset of +5, well, if we were to look and find address 645, we would see, in fact, that hex 645 corresponds to the label that we want, port C outset. So in this case, the disassembly, even though it's a little bit of a roundabout way, actually exactly does what we intend for it to do. It points and references that relevant memory location. So again, a little roundabout, but ultimately it will do the same functionality that we intended. And likewise, I'm not going to see these other two C lines of code, but I will go down to this portion where we wrote from, where we continually loaded port A in into port C.out. What it does here is it does something similar. It loads the starting location of port C registers, which again it corresponds initially to port C dir, and then it loads hex 600 into this pair of registers R18 and R19, which if we were to do some digging would correspond to port A.dir, and then again uses this move word instruction of this starting location for port A into the Z pointer, and then using the Z pointer, it then offsets from port A.dir +8, which I actually will look up for us if we were to type in 0x0608, we would see we have port A in, which is exactly the memory location we want to access. It loads that into register R18, that value at that memory location. And then it moves word R24, R25, which again, port C.dir. And then it stores port C.dir plus 4, which again, correspondingly, I'll help us out, look this up, 44, goes to port C.out or port C out. And it stores whatever was loaded from port A.in. So this is exactly, again, what we wanted to, functionality-wise, what we wanted to be accomplished with our assembly code. But again, if we were to write this code ourselves, we would probably write it in a more efficient manner. Now, again, this is ultimately due to the optimization of the compiler. So let me demonstrate that by now, if I stop my debugging and change the optimization level of the compiler, let me just bump it up all the way in terms of how much optimization is performed and go to optimize most, and then rebuild my program, and then open up the disassembly tab again. I have to first stop it to actually witness what's in the disassembly tab. And now we're to look at and find this section of code again, relevant to my C code that I wrote. I were to look and see, let's say the port C outset C code again. Right away we can see, wow, it went from, I think, 4 or 5 lines of code down to 2 lines of code. And what's it doing now? Well, it's setting R24 to be hex FF, and then it's directly writing, just as we would, to the memory location hex 645, which corresponds to port C outset, and then it writes that hex FF directly to that memory location. That's great. It simplifies it so much more, and it actually is accomplishing the manner in which we would write the assembly code. And then likewise, if we were to go down to this port C out equals port A in, it directly uses LDS to load from port A in into R24, and then stores directly to that memory location, port C out, hex 644, whatever was loaded into R24. And I didn't mention this actually, I meant to previously in the other optimization or the other disassembly file, but it doesn't show us this whole while loop that we created in C code. We actually have to look at the assembly code to see how it does it. It implements this rjump functionality just as we would in assembly. And it jumps to the program counter, which is labeled PC. It jumps to the address associated with PC minus hex 4, which if we were to do some math and see from address 11B, 4 up should put us at 117. So here, doing this rjump program counter minus 4, which again, in our case, we would usually use a labeled instead of directly calculating what offset from the program counter we need. But in this case, it ultimately implements this kind of looping nature. We jump back up to this line of code, and then it does this over and over and over and over, forever and ever. So in this case, exactly what we would implement with most optimization, and unfortunately not what we would implement with no optimization. But nonetheless, that's just a necessary evil and a consequence we're going to deal with for the purposes of this course, requiring that you all turn off optimization. So make sure again that you all do that for every program for every project within Atmos Studio that you all create. But that's just interesting, and I wanted to show us how our C code's actually going to be get generated into assembly code relevant to our microcontroller, and start seeing how that actually happens. And the compiler is the thing that's doing that. So sometimes later on we're going to look at disassembly, but probably not much in this tutorial series. But nonetheless, that's pretty much all that I wanted to cover for this video. I'm going to go ahead and wrap up here. But in future videos, I'm going to start getting into more specifics regarding the C programming language. Again, for this video, just wanted to start seeing how some introductory program in assembly would get translated to C. So let's go ahead and start doing some more detailed oriented content regarding the C programming language in the next video.